Okay, in this video, I am going to walk you through the calculations for our spectroscopy experiment. So I'm going to just go through the slides and provide example calculations, which will hopefully help you as you work in your groups through this project. So the first thing we're going to do is work with our A solutions. And the A solutions contain a limiting reactant, so a reaction does not reach equilibrium. So I can see I've got 0.2 molar iron nitrate and 0.002 molar KSCN. So the KSCN is your limiting reactant because the molarity is much smaller. We also have a smaller volume as well for each of the A solutions that we're going to make. So after making the A solutions, we're going to calculate the molarity of the product using stoichiometry. So this is a good review from Chem 60, Chem 101. And again, because it's a limiting reactant problem, and I know my KSCN is limiting, I'm going to be using the KSCN as my limiting reactant. And I'm going to give you an example of A2. So the final answer was provided for you so you could check your work. I'm going to use this as an example to go over the stoichiometry. So I'm starting with my 1 mil of the KSCN. So 1.00 milliliters of KSCN. And I want to get the product, which is my red FeSCN2+. So I'm going to start with a mil of KSCN, looking at the solution map KSCN. And I'm going to go from milliliters to liters of KSCN to moles of KSCN, because remember I go from liters to moles using molarity as a conversion. And we're given 0.00200 molar KSCN. And remember, molarity is a conversion factor in hiding. So this is the same as 0.00200 moles of KSCN for every 1 liter. So that's the conversion factor we'll be using there for molarity. From moles of KSCN, I can go to moles of SCN minus. Chemical formula as a conversion, I can see it's a 1 to 1 mole ratio, because for every 1 mole of KSCN, I've got 1 mole of SCN minus. And then I can go from moles of SCN minus, right, to moles of my product, because it's a 1 to 1 mole ratio. And our goal is to get molarity. So molarity, I like to think, is a 3-step process. 1, find moles. 2, find liters. And 3, divide moles over liters. So let's go ahead and set this up. So I have my 1 mil of KSCN, and now I can convert from milliliters to liters, because I know for every 1 liter I have 1,000 milliliters. And I can see my mils cancel. And now I'm going to convert from liters to moles using molarity. So I need liters downstairs, so 1 liter, and my molarity, 0.00200 moles KSCN. And now I can see my liters cancel. Oops. And now I have moles of KSCN. So I'm being very thorough with these conversions. 1 mole of KSCN for every 1 mole of SCN minus. And I can see my moles of KSCN cancel. And now I'm using my mole ratio for my balanced chemical formula. For every 1 mole of SCN minus, I have 1 mole of my product FeSCN2+. And those units cancel. And again, these numbers came from my balanced chemical equation. So for every 1 mole, right, that's the number 1 right there because there's nothing written. I've got 1 mole of SCN minus, which would be right there. So let's put this into the calculator. So on the calculator, 1 divided by 1,000 times 0.002, enter. And I can see I have 2 2.0 times 10 to the negative 6 moles of my product, FeSCN2+. So that's step 1, find moles. Step 2, find liters. So here, looking at the liters total in the solution. So liters total in test tube A2. So when I look at that, I can see I have an A2. I've got 25 plus 1 plus 74. That is indeed 100 milliliters. So 100.0 milliliters. 1 liter contains 1,000 mils. So 100 divided by 1,000 gives us 0.100 liters. 1.000 liters. And now step 3, divide to get molarity. So my molarity of my product equals 2.0 times 10 to the negative 6 moles divided by 0.1000 liters. And that is indeed where we get that 2 times 10 to the negative 5th molarity, FeSCN2+. So that is an example of how to get the molarity of the product for test tube A2. Now go ahead and work on the same thing for test tubes A3 through A7.